We're in chapter 5, at least for the recommended text. So I would recommend it at a minimum, looking through it. I don't know that I'm going to assign to be a reading assignment. That doesn't mean you shouldn't look at it. Okay, so I'm trying to find the beginning, which is right here. So this is right here. There it is, chapter 5, energy. This is where we're at, page 119. I'm going to review the concept of work. You see that that's the first topic that they in your typical physics problem. I'm sorry, in your typical physics textbook. I'll go over that with you. Some formal definitions and formula that are useful, I'll certainly review with you. Describe also what work actually is conceptually, how we calculate it, how it relates to energy, why is it in the energy unit. I'll also be talking a little bit about second section, which is the work-kinetic energy theorem. A fancy word for a very simple idea, in my opinion. It's pretty straightforward, generally, but I will go over that part today. And then I will be also discussing potential energy, gravitational potential energy, as well as elastic potential energy. Potential energy is stored energy, some sort of stored energy that's stored. Can be in a battery, which you would consider electric potential energy. That's the energy stored in your battery. You can have a magnetic potential energy if two magnets are pushed very close together, but they're repelling. Technically, if you release them, they kind of fly apart because of their repelling force. That stored energy, once they're pushed together, would be called magnetic potential energy. You have electromagnetic potential energy. It's a kind of a combination of electric and magnetic fields. You can have gravitational potential energy, which you certainly need to know about. You can have chemical potential energy and nuclear potential energy, all energy stored inside of the nucleus of a variety of different atoms that can be unleashed if you cause it to have a chemical reaction with something else. Anyways, potential energy is always some sort of stored energy. The one primary one that you have to know is potential energy as it relates to gravity. Also, elastic potential energy is the energy stored in something that's flexible, something that you've deformed in some way. Generally in physics, AP Physics 1, it's the spring. You finally get to return to Hooke's law, like I said we would, as it relates to the energy stored in a spring when you compress it, stretch it out. So I'll talk about a little bit about that today. Yep. Whatever you need to do. Yep. We're going to talk about kinetic energy a little bit today. Kinetic energy. And then maybe even a little bit about conservation of energy. So I'm going to try to, again, do an example of many of the big ideas that belong to this unit. So conservation of energy is something we'll talk about too. All right, so let me begin that. Now in this class, everybody has taken physics before. In the other class, I think I have a couple that had never taken physics before, but all of you have taken it. You've all seen some bit of topics, and all been part of some sort of period when you were younger as freshmen where I taught you about energy. So, some of this will come back to you. All right, I'm gonna shut that off. Okay, so let's start with work. So work in physics, this is section 5.1 again. Work in physics is really a process that scientists and engineers refer to involving some sort of energy transfer. if you're transferring energy to something, then we'd say you. It doesn't have, when I say you, I mean, it doesn't have to be a person, of course. It can be, the wall. You plug in your wall at night, plug your battery into the wall at night. The wall is technically doing work. Wall is technically doing work on your battery because it's transferring energy to your battery. It could be you. I mean, it could be you pushing something. If you're pushing it, you're transferring kinetic energy to it potentially. That would be an example of doing work. You could be climbing a hill where as you climb the hill, you're technically increasing your own potential energy because you're getting up higher and higher. So another example of doing work, you're technically starting to store some of your energy, potential energy. But anytime there's a movement of energy from one thing to another thing, that process is an action. It's a verb, not a noun. And that process is referred to as work. The first one would be called, let's call it positive work. That's the process of adding energy to a system. And it can be any type of energy to a system, or it doesn't have to be a system, but we'll just talk about it as a system. Any type of energy to a system. Any type of system, when you add energy to it, we call that positive work. In contrast to what we might call negative work, which is a process of removing energy from a system. Again, any type of energy, called negative work. Some common examples of positive work. Throwing a baseball. Why do you think throwing a baseball would be considered positive work? Yeah. Yep, and since you're accelerating it, what's happening to its speed? Yep, and since its speed is increasing, what's happening to its motion energy known as kinetic energy? It's going to go up, yep. So that's a process of providing kinetic energy to something you're throwing. Could be a baseball. That would be called positive work because you just transferred energy to the ball. Climbing a hill. In this case, again, you're not transferring energy or providing energy to something as necessarily motion energy, certainly not increasing your speed, but you're getting higher and higher in the air, then you're increasing your potential energy. Still a transfer of energy. Pulling something, pulling or pushing something. Pulling, pushing, / lifting something. Those are all just common examples of positive work. Even a microwave does positive work because it adds thermal energy. So you should, and actually, let me just point that out. We have to deal with gravitational potential energy. These are energy types that you have to be familiar with. I don't want to write that because it just takes me too long. But you might want to. G starts for gravitational potential energy. These are types of energy that I'll reference during today's class. Kinetic energy, K.E will just be short for motion energy. Elastic potential energy. That's stored again in something that can be deformed, like a spring, even a diving board, any elastic band, any bungee cord. Anytime you stretch something or make it turn into some particular shape that it doesn't naturally want to be in, and you hold it in that deformed position. If you let go of it and it snaps back to its original shape, then you know that there's got energy stored in it. Like I said, a diving board technically bends, and we know that energy gets stored and then it releases itself, transferring energy from potential energy stored in the board to you as kinetic energy, which then turns back into potential energy, gravitational potential energy to go up in the air. But anyways, anytime you're looking at something that's elastic, that can be bent or deformed, spring, elastic band, any bungee cord, anything like that. That's called elastic potential energy. So negative. So what I was saying was a microwave. Oh, sorry, that's the other one. Thermal energy. Thermal, put in parentheses, heat energy. So heat is certainly a form of energy. I will point this out. I guess maybe I'll do it right now. Thermal energy is actually kinetic energy of atoms and molecules. So sorry, I lost my atoms, and atoms move around quite a bit. We don't actually notice it at all. But every atom and a molecule in the air, primary nitrogen in the air that you're breathing right now, but obviously some oxygen, carbon dioxide, and others. But they're all moving. You don't notice that. You feel like you're in stationary air. Actually, on the most microscopic atomic level, if you could see all those atoms in front of your face, they're actually zipping around at extremely high speeds. Some of them can be literally moving 1,000 miles per hour. You might say, well, why doesn't that produce wind? To have wind, you have to have all of the atoms moving in the same direction. Then you have an aggregate effect, a cumulative effect of all of them moving like a fan, right? They're all moving in the forward direction, and you would feel that. On the other hand, when you look at atoms and molecules that are in the air, if you could, for every one that's moving, let's say, to the right with 1,000 miles per hour of speed, there's another one moving to the left with 1,000 miles per hour of speed. And for every atom you see moving up, there's another one that's moving down. And they're literally jittering, moving all over the place. As you get warmer, as you warm a gas, it actually increases its kinetic energy. They start moving faster and faster as they get warmer. We call that heat energy, but I'm pointing out that heat energy is actually, on the atomic scale, a form of kinetic energy. Most people probably may not know that, but that's 100% true. As you cool a gas down, or even material down, even like at this table that I'm touching right now, if it has some temperature to it, which it does, if I could zoom in on a molecular scale, I'd actually see that each atom is kind of vibrating like this. Think of it as just like a little circular thing. It vibrates back and forth. It's not moving necessarily left and right because it's part of a solid. It can't. But they stay in one spot, connected to another atom, connected to another atom, but each atom literally vibrates back and forth. So even solids, as you heat a material, they start vibrating more and more quickly. So it's a form of kinetic energy. And then as you cool them down, they start vibrating less and less quickly. So in all cases, even if it's free to move like a gas or a solid, any heat energy is a form of motion energy on a molecular scale. Just pointing that out. Okay, so let's do some, so I guess I was saying like a microwave. Microwave would be positive work, adds heat energy to something. A refrigerator does negative work. Technically, a refrigerator removes heat energy from something. When you put it in, it cools it down and it absorbs that heat and then pushes that heat outside of the refrigerator. So it's technically a negative work machine. While a microwave, I guess, would be a positive work machine. Those are some less common examples. For negative work, actually, really friction is the main one that you have to know about. What are some common things where energy is removed that comes up in the AP exam? Friction, for sure. They're going to mention friction in a problem that references work, and you need to know that friction is always removes, I should be more specific, kinetic friction, kinetic/sliding. Whenever something's sliding across the floor, it's losing energy, right? We know it slows down because that heat, that kinetic energy is being turned into heat from the sliding effect. Just rubbing your hands together, creates some warmth. So if you push a book across the floor, or even a more extreme example, a car that's flying along, for example, at a high speed in the parking lot, jams on its brakes and skids along skid mark. If you were sitting in the parking lot right next to that wheel as it flew by you, of course, being so careful not to get run over, the moment it skids by you and it's making that black mark on the pavement, if you instantly put your hand down on the pavement, you'd feel warmth. It would only last for a fraction of a second, but you'd feel the effect of that the pavement feels a little warmer for a brief moment. So that's evidence that kinetic energy, when you're sliding something along a frictional floor, yeah, the car is losing speed and losing energy, but where is it going? It's turning into heat. It's turning into heat for the air around the area where the skid is being created, skid mark is being created, and the surface itself of the asphalt would warm up. It's not like the universe loses energy. The universe can't lose energy. That's the concept behind conservation of energy. Individual things can lose energy, but when one thing loses energy, something else must have gained it. So if a car is skidding along and then stopping, clearly it lost its kinetic energy. Where did it go? It had to turn into some other form of energy, into heat. All right, so let's an example, a very common starting example. I'm going to draw this out as like this. This is usually the good starting point. In fact, the textbook agrees, because I think one of the first images they show in the textbook is this one. It's not just your textbook. They all pretty much kind of have the same format. All textbooks in our entire planet all kind of have the same sequence of things that they talk about and show you. So this is something you would see. So let's just say it has some mass. It starts at some initial position, 0. And it's, starts at rest, as always is the case, nearly always is the case. And then it's being pulled some distance to, I guess, over here. But it's a constant force. F and theta are constant. Don't have to be, but they could ask, what would happen if the angle changed while it was pulling? F is constant. Direction of pulling is constant. And they might ask a question like, how much work is done by the applied force? This is the wording they use. How much work is done? Because remember, work is not a noun, it's a verb. It's not something you can hold or have, it's something that you do. It's an action, it's a verb. So if you were pulling this, if this was a rope, and in textbooks it might even show a guy pulling it as with a rope going in that direction, and they say, how much work did the man do? What they're referencing is how much energy did that man transfer over to the block while he pulled it from the first position to this next position. I'll also point out, maybe on the side, that energy is measured in joules. And so is work. The unit for energy and work is joules. They're the same unit because they're the same quantity. Similar to, what gets transferred in our world. Well, you could say money. Money is a currency, gets transferred in our world. You say it's true. What is the process? What process has to happen for money to be transferred? Not surprisingly, it's called work. When you actually do work, it has some value. If you did 10 hours of work, someone say, what is the value of that? And what unit to use? Dollars. I did $100 worth of work. I worked 10 hours for you, and you pay me $10 an hour. So the unit for my work is dollars. And they say, okay, how much money did they actually give you once they put it into your pocket? Dollars, $100. And, so the unit for work is dollars, and the unit for what they actually put in your pocket is also dollars. Yeah, that sounds about right. Yep, they're both the same. So in a similar way, energy and work, they both share the same unit. If I pushed you and did 5 joules of work on you, and then I said, how much energy does this person now have after she was shoved? Mr. Kurtzak did 5 joules of work. She must be moving with 5 joules of energy, I guess, because I just transferred 5 joules of energy to that person by doing 5 joules of work. So just know that's how they word it. Work is done. How much work is done? So what is what are the details? I will tell you. In fact, I'm going to add something to this right here. For positive work, a force or a component, and I'll explain what that means in a moment, or just a component must act in the direction of motion, direction v, the velocity. So for positive work to occur, a force or just a component, which I'll describe in a moment, must act in the direction of motion. For negative work, a force or just a component, which again I will describe, must act in the direction that's opposite to the direction of motion. So if you're in a supermarket and you're pushing the cart well forward, that's what we all do, right? And you're pushing it hard enough and it starts speeding up, you're doing positive work on the cart because the direction of your force is forward, and it's while it's moving forward, well, that's positive work. You should be transferring energy over to the shopping cart. If a little 90-year-old lady all of a sudden walks out in front of you, of course, you wouldn't continue pushing forward at that moment. You would quickly decide to change the direction of your applied force on the handle, immediately beginning to pull backwards. And any backward force that's in the direction that's opposite to the forward direction would do negative work. You're going to remove energy from the cart and it would slow down, right? Yes. You're a step ahead of me, so hold off just 1 minute. I'm gonna attack that question. Question was about gravity force and normal force as well. So let's just look at our little, my trusty robot. I've been using him for so many years. So positive work. The direction of motion is to the right. You guys in class can't see the speedometer, sorry. But the speedometer is now, reading something. It has some kinetic energy, some motion energy. The amount of kinetic energy this box has depends on how much work he did. The detail about how much work he did is that while he's pushing, how much work he does is equal to how much force he applies and the distance it moves while he's pushing. I'll say that again. Let's just say that we start over. And let's just say he pushed it 2 meters. Here's 500 newtons of force for 2 meters, and then he lets go. And we say, okay, how much work did he do? Well, it's the 500 newtons of force that he was just applying, because work is force times distance. How far did he push it? 2 meters before he let go of it. Okay, so 500 times 2, 1,000 joules. So he did 1,000 joules of work in that 2 meters. How much kinetic energy do we think the block would then have? 1,000 joules, exactly. He did 1,000 joules of work. Well, it has 1,000 joules of kinetic energy here. That is the concept behind fancy wording called the Work-Kinetic Energy Theorem, which just means that if he did 1,000 joules of work as he pushed it, then that 1,000 joules turns into kinetic energy, and it now has 1,000 joules of kinetic energy because energy was transferred from the man to the block while he pushed it, and the amount of, whatever force times distance is. So work is a force times a distance. Again, if the direction of motion is forward and the force is forward, positive work is done. And the speed will increase, and so will its kinetic energy. However, negative work is the opposite. A force has to be in the leftward direction while it's moving right. This is negative work. Positive work. Friction. Negative work. It's removing energy from the block as moving kinetic energy, turning it straight into heat. So in the simplest case, you end up with a force that's fully in the forward direction or a force that's fully in the backwards direction. And then it's simpler. Once you end up with angular forces, which I'm going to tackle with you in this problem, it's a little more complicated. So let's take a look at what that really means. And then I'll have you down the formula. And it's on the equation sheet. AP equation sheet will have it for you. But work in general is a force times a distance. But this has to be in fact, that's, cross that out. It's not really correct. I'm going to write it as work. I'll maybe do it on another piece of paper. Work is really the magnitude of how much force you're referring to times the magnitude of some displacement. And this is W stands for work. And we'll say applied. We're talking about the robot. You can technically use the work formula for anything. If this was how much work is done by friction, then this becomes the force of friction times the distance it slid while it felt friction. They could say how much work was done by the robot. This becomes the force from the robot times the distance it moved while the robot was pushing it. So in general, it's a force times the distance. Technically speaking, though, if you end up having some sort of angled force, like we're going to tackle in this problem, only the force that's in the direction of motion is actually transferring energy. So if we move the box from one point to another point, the displacement vector technically goes from like this. This is displacement. It's actually a vector. Putting a vector symbol over the displacement vector, because the displacement vector technically starts wherever the object begins and ends wherever the object ends. Assuming that it's, moving along at that point, passes through that point, but we call that the at that point. That's called the displacement vector. This, on the other hand, is the x component, and that's only this amount of force in the direction of motion. So when we go back to that simple definition, which was work is force times distance, it's kind of very loosely stated. Really, it's the amount of force in the direction of motion multiplied by the distance you actually traveled while that force was applied. So how would we write that? In a textbook, it's written this way. This is what it would say in your textbook. These are multiplications of force, cos theta, and delta x. Now, most textbooks don't necessarily do the best job at describing this. Some of them do, some of them don't. If this angle here is theta, and the magnitude of that force is F, what is this quantity F cos theta? How does just F cos theta relate to something in here? What would F cos theta be? Good job. Yep, totally. Fx is F cos theta. Nice job, Jaden. Fy would be F sine theta. Because again, opposite goes with sine, adjacent goes with cosine. So technically, Fx is this expression F cos theta. And instead of writing Fx here, which you could do, I don't mind doing it, times how far delta x is the physical in magnitude, that's just the, the distance, the length of the displacement vector, right? Again, this flies by this point, but they would say, how much work did the robot do between point A and point B? How far was delta x? Oh, that's just this number, 5 meters, I don't know. Fx technically is this amount of force, however long this piece is. This amount of force, this does no work. Because again, to do work, it's only the force that's in the direction of motion or the force that's in the opposite direction of motion. If I said, how much of this vector is pointing rightward? How much of this component is pointing rightward? None of it, yeah. So how much work did this component do while, again, it was applied to this box as it moved from here to here? That component did nothing, did no work. How much work did this component do? We'd have to work out how much force that is, and we could certainly do that and then multiply it by that distance. So forces that are vertical when something's moving sideways don't do any work. It comes back to your question, Jaden, which was a very good question you asked early on. As something is sliding, which direction is the normal force? It's up, and the direction of gravity force is down. If someone said, hey, it literally slid from A to point B, and we called that the displacement vector, and they said, how much work did the normal force do? You would use the same formula. Work done by the normal force equals the magnitude of the normal force, cos theta, times the full distance. However, what does this theta represent? It's the angle between whatever the vector is that you're referencing, this formula. Here we're talking normal force, so it's the angle between the normal force vector and the displacement vector. Well, what is the angle between a vector that's pointing to the right and the Fn, which is pointing up? What is the angle between those? 90. And if you plug in cos 90 into your formula, into your calculator and hit enter, it's going to say 0. It means that this zeroes out, saying there's no work the ground doesn't transfer energy to a car while the car is on a flat road. It just doesn't. The engine does. The engine is providing some positive work. Any air resistance and frictional forces, which are straight leftward while it moves rightward, they'll do some negative work. But forces that are perpendicular to your direction of motion don't do any work. Of course, if the hill was tilted, then do you have some gravity force that's going down the ramp in the direction of motion? If this was a ramp now, you'd say technically, yeah, that's the good old mg sine theta. But fgx is now in the direction of motion, so now gravity's doing some work, transferring some energy to you. You're going to speed up. But on a flat road, again, gravity and normal force do no work. There's no work. So worth commenting, I'd say, for you. No work done. It's easy to get points on that if they give you the free response question for sure. No work done by Fn or Fg when moving on a flat surface. Why? There's no component of those forces in the direction of motion or in the opposite direction of motion. They're 90 degrees to that direction of motion. There's no way that can work. So let's come back to this one here. How would we now do this? We'd say the work done by the applied force is however much applied force there is, which I haven't even told you what amount it was. I don't know, let's pick a number, 100 newtons. So I just decided to make that pulling force 100 newtons. And let's put a distance in. Let's just call it 5 meters or something. And let's call this angle here 30 degrees, let's say. Maybe you can try it. How would you now try to utilize this formula, which in this format that you're seeing it right now, it's typed onto the AP equation sheet looking just like I've written it here. How much work is done by the robot, the applied force, whatever is pulling in this direction? Give it a try. Maybe even challenge yourself. What if you didn't have a calculator? Could you still calculate this using your 30, 60, 90 triangle? Is that tool still in your bag? If so, how sharp is it? Maybe you want to try it again, because it will be necessary at the end of the year potentially to answer certain multiple choice questions using the 30, 60, 90 triangle. I always recommend drawing it. And the numbers are 1, 2, √3. And then you have to assign the largest number to the longest line, smallest number to the shortest line, and then add your angles of 30 and 60 in there. Right, because technically you're being asked to do cos 30, right? Most students would just take out a calculator. Yeah, let's see if you can do cos 30 on your own. What is the cosine of 30 degrees? Let's try it. Or is it? A bit louder, sorry. The force in the magnitude for the applied force was 100 newtons. I added that right in the end, sorry, that wasn't clear. 100 newtons of pulling force in that 30-degree direction. And yeah, there's vector symbols. I mean, I'm not always the best with that. I mean, a textbook would have little vector symbols over those, whatever. It just doesn't really matter that much. But technically, that's how it would be shown in a textbook. So let's just see how it goes with this triangle. 1, smallest number, goes here, shortest line. 2 is the number, goes with the longest line, because these are distances, right? These are physical distances. And √3 has to be the other one. The thinnest angle is, of course, 30 degrees. the wider angle would have to be the 60-degree. And the 90-degree, well, nobody cares about the 90-degree angle. Only depends, it really only care about the other angles, not the right angle. All right, so we said, what is cos 30? What is the definition of cosine? What divided by what? Using words like hypotenuse, adjacent, and opposite.
Opposite over hypotenuse.
Good guess. But cosine will actually be adjacent. It's close. Adjacent over hypotenuse. And then sine is opposite over hypotenuse. So cosine is adjacent over hypotenuse. If you're not sure, you could always do the SOHCAHTOA thing. I never knew this, So, but I went through school and I've never heard something such a thing until I became a teacher and students said, "Don't you know SOHCAHTOA?" And I said, "I have no idea what you're talking about." But it works. S stands for sine, is opposite over hypotenuse, OH. C stands for cosine, which is A adjacent divided by hypotenuse, and tangent is opposite divided by adjacent. Does that help? So let's find, we're asked to calculate cos 30. Yeah, I know we could all put in our calculator, get that, but I want to see, can students do this? Cos of 30, we say, all right, where's our 30? There it is. We just have to figure out what leg it is adjacent. Adjacent means alongside of, to alongside of. This is adjacent to the 30-degree angle. So root 3, that's what adjacent is, root 3, divided by the hypotenuse, which is 2. Right, so that's what cos 30 is. Cos 30 is root 3 over 2. Do I memorize that? Certainly not. Waste of my time. Even after all these years, right? After all these years, waste of my time. But if you need to figure it out, that's my tool. That's my little multi-tool that I use. So technically, when we do 100 times 5, we see that the answer, this would be 100 times 5 is 500. And you could type it in, cos 30, into your calculator, or you can say root 3 over 2 just to convince yourself that it gives you the same number. I don't know what it is, but let's figure it out. 500, just make sure if you're doing the cos 30 that you're in degree mode. 433. Approximately. I don't know what that's 433.01, I guess. Now, what unit would that be? Joules. We just did a work calculation. How much work did whoever is pulling this rope or whatever, nobody cares either about that, but whatever is applying this force, how much energy did it transfer to the box as the box moved from here to here? That would be 433 joules. Again, if you were doing, they said how much work is done by the normal force? You'd say, okay, it's the magnitude of the normal force. Again, that theta represents the angle between the force vector that you're interested in evaluating for work and the direction of motion. So that would be 90. Cos 90 degrees, and you can put delta x. And it doesn't matter because cos 90 is 0. That's how you would defend yourself on an AP exam if they said, yeah, you stated 0 joules, but what equation would you use? How do you use it? 90 degrees because, again, that theta represents the angle between whatever the force is that you're using in this formula and the direction of motion. You could say the same thing for gravity. Work the force of gravity is the gravity force and magnitude, mg. And the direction between the gravity force, which is down, and the displacement vector, which is a down and a, right, gravity is down, displacement vector is my blue marker, it's 90 degrees also. You would show that this, when you put in cos of 90 there, it's 0. The whole thing becomes 0. Now we might wonder, how much kinetic energy does the block have? If the robot releases the block right here, how much kinetic energy do we think the block has? It's going to continue coasting at that point. Maybe there's no friction. This whole problem has been a no friction problem. So if he did 433 joules of work as he pulled it from here to here, and then let's go, how much motion energy, how much kinetic energy do we think it would have? So as he, again, on a frictionless surface, which this problem was, again, I do an angled force, but if I could, I would. He pushes, 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 and then for 5 meters, and then he releases it. And we say, okay, how much work did he do? 433 joules. Okay, how much kinetic energy does the block have as it slides along the frictionless surface? He did 433 joules of work. Anybody? Yep, 433 joules, totally. Yep, he transferred 433 joules over to it. Technically, if this was a real person, you'd be digging your feet into the ground and right, pushing, pushing, pushing. Would you potentially sweat from it? Oh yeah. Could you technically lose weight if you did that all day long? Yeah. Does that mean that you're losing calories? Yeah. Is calories energy? Yeah. So does that mean while you push this box, again, you're technically losing energy and it can result in losing weight? Yeah. Where does the energy go? If you lose energy while doing an exercise and your exercise is pushing this block, it's being transferred to the block as kinetic energy. Technically, on a surface, that would be a very difficult exercise, but we ignore that. Okay, so now I'm gonna ask you to do another part to that. Next question is determine the speed. Determine the speed of this block coasting along. Remind you, and it's been a long time, I know, that kinetic energy as a formula is 1/2 mv squared. Kinetic energy depends on mass and speed. It's not, you should know that it's not a vector. I always wanted it to be. I always wanted kinetic energy to be a vector. I always said, why not? You're driving forward, can't you say my energy is in the forward direction? Like, hey, V makes sense to say my direction is forward. Why can't we say kinetic energy is forward and call it a vector? I don't know why, to be honest, never got a good answer for that when I was a student. But it's not a vector. It's a scalar, just a number. Number, no direction. Which means this V is not velocity. This V is just speed. And M is just mass. That is the formula for kinetic energy. So give it a try. With what speed is the block moving? This was on a frictionless surface. After being pushed, I don't know, what was it, 5 meters. Take the mass, I'd have to give you a mass. Take mass as 10 kg. Which matters, this matters. But I want you to think through the steps here. It's sitting on the, the rest, at rest, man starts to push. What is the mechanism for applying, for transferring energy? Applying a force in the direction of motion. It can be a component or it can be all of your force. And continuing to push while it moves through some distance. That's how you transfer energy to it. When you release it, it now has that kinetic energy, however much work you did, as it coasts along, just like you saw in the sim. And as it continues coasting, what is its speed? This is all a continuation of that first problem. You'd have to come back to how much work was done. Remember, it was 433 joules of work was done. All for speed. And I'm doing this problem, it's going to have multi-parts, but it's at least going to expose you to work, kinetic energy. In a minute, I'm going to have it go up a ramp, and you're going to have to calculate how high it goes, with at least expose you to potential energy today. And the conservation of energy will kind of come into play in a minute. But it's just, my plan was to just do a multi-step problem that exposed you, in best case, to all the ideas in one problem. That was my plan. So just come along with a ride. You can also think, how is the speed affected by the mass? We can come back here, right, and say that we could start over, and we make it a small, block with the mass of, it's a 50 kg, and push it for 5 meters. and see that it has a pretty good speed. However, does the mass affect the speed that it has right now? Well, we could certainly bring a refrigerator in there. Now it's got not 50 kilograms of mass, but 250, and he can push it the same 5-meter distance. Will it still have the same speed after he's pushed it for 5 meters? Let's just say that was the 5 meters. You'd say no, right? Has much less speed. So, it's kind of intuitive. Something that's massive is going to speed up less slowly. Newton's second law, right? Acceleration and mass are inversely proportional. The interesting thing for you to think about, let me ask you this question, though. This is an interesting question. Notice that the robot, it says how much newtons he's pushing with. His maximum pushing force is 500 newtons. So let's just say that I have 5 meters taped out on this. I wish they made the distance measurable on this app. It would make it so much better, but they don't have that. But whatever. So I'm going to push with 500 newtons of force for 5 meters and then let go. And let's just say that, well, how much work did he do? 500 newtons times 5 meters. So that's 2,500 times 5. 2,500 joules of work. How much energy does it have now? 2,500 joules of kinetic energy. If you bring it back, when you do it like this, it's a tricky question, so be ready for it. And I now push again with 500 newtons of force for, again, 5 meters. And then I release it. We clearly see it has less speed, and we ask the same question. How much kinetic energy do those blocks have right now compared to the previous answer? It's the same, yeah, it's the same. Totally counterintuitive. You're like, wait a minute, it's moving slowly. I'd say that's true, but kinetic energy is actually 1/2 mv squared. So even though there's less v, it's making up for that with more mass because it's mv squared. 2 of those quantities are in there. That's totally counterintuitive. You could do that by saying, well, did he push with 500 newtons of force just now? Yeah. Did he push the same distance of 5 meters? Yeah. So I guess how much work did he do? I guess 500 times 5, 2,500 joules of work. So how much kinetic energy does it now have? The same as before. So even though the little block is moving faster, it has less mass. The heavier block has, well, of course, more mass, but less speed. And in both scenarios, they're moving with the same energy, not with the same speeds, but with the same kinetic energy, which is interesting and hard, kind of counterintuitive. Okay, so how would we do the speed calculation? Maybe you, maybe you want to be familiar with solving it for v. Multiply both sides by 2. We did this the other day. 1/2 times 2 cancels. Then I have to divide by m to both sides. M and cancel. Then I have to square root my v. So I end up with v equals the square root of 2k over m. So what that means is if they give you a problem and you know how much kinetic energy it has and you know its mass, you can plug that in. Do I recommend you memorizing that? Definitely not. But being able to manipulate the kinetic formula, or the kinetic energy formula, somewhat useful for sure. So what do? 2 times 443, because that's how much kinetic energy it had, because that's how much work the man did. What was its mass? Did I say 10? Oh, I said it right here. Yeah, 10. So I get 2 divided by 5 is really 1. Sorry, 2 divided by 10 is really 1 over 5. All right, 9.3, I get approximately 9.3 meters per second. A little under 10 meters per second would be its speed. In 1 second, it should coast a little under 10 meters per 1 second. Next question. Now it's moving along. And let's just say it hits a rough patch. So it's moving along. Here it is with a speed of 9.3 meters per second. And it hits a little bit of a rough patch there. And we know, let's just say we know the distance of that rough patch is 1 meter. And we know the coefficient of kinetic friction is, let's just say, 0.5. How much work is done by the friction force during the 1 meter? Just meaning that energy is going to be transferred. Positive work means the frictional force is going to give extra energy to the block and speed it up. We know that never happens. Negative work indicates that the frictional effect in here is going to remove some energy from it, down. We know that happens. And turn that energy into heat. Work done by friction force. It's the same format. I want you to know that. The general template format is F cos theta times some distance. This is like a template for that formula that's on the AP equation sheet. For the friction force, you'd have to say it's the magnitude of the friction force. Now you'd have to think cos theta. That's the direction between the force that you're talking about, which we know is to the left. Friction force is leftward when it's in this friction area, while the displacement vector is actually to the right. So what's the angle between a vector that's to the right and a vector that's to the left? Good job, Jaden. 80 degrees, totally, yep. Any vectors that are in opposite directions of each other, we would say that the angle between them is 180 degrees. If they're in the same direction like this, we'd say that the angle between them is, we'd say that the angle between them is 0 degrees. So two vectors in the same direction, theta is 0 degrees. Two angles in opposite direction, theta is 180 degrees. Of course, they're at right angles to each other. We'd say 90 degrees. So when you do a frictional kind of part to this type of problem, you're putting in 180 in for cos and for cosine. Because the frictional force is to the left, direction of motion is to the right. See if you can try it. Try. Now you have to be like, oh God, I have to remember the frictional force. Well, yeah, you could do it though. Frictional force is mu times Fn, right? Frictional force in general is some coefficient of friction times normal force. Also on the AP equation sheet. Notice I gave you the coefficient right here. And you'd have to think, well, what is the normal force and how does that relate to the gravity force through maybe a free body diagram? Once you develop the frictional force equation, that has to get stuck right there. What's that? I think it's a 10 kilogram. Yeah, 10 kilograms. Give it a try. Again, my goal is to literally expose you to like all the possible things. You'll see that after this whole thing that I do with you. You end up seeing snippets of all of these things that I'm showing you normally in multiple choice questions. Frictional parts where they mention work, or angled forces where they mention work. Kinetic energy is mentioned. Going up hills, which I'm going to do in a minute with you. And I expect to learn all of it today. I'm just again trying to expose you to the ideas. And remember the delta x there, that's delta x, that's 1 meter. That's whatever distance they said that it travels through a frictional surface. You can do it, totally can. If a student does get hung up, I think they're going to get hung up with the frictional force part. But just remember that on a flat surface, even if something's moving on a flat surface, gravity is down in the amount of mg, the normal force is up in the amount of mg, right? Because they have to be balanced. since it's not moving up or down. And that's totally needed for frictional force, that concept that the normal force is actually equal to mg. Totally necessary knowledge. All right, let's see, how does this play out? In for the frictional force in magnitude, total quantity of force, sliding friction force, it would be, I guess, a mu, the coefficient of sliding friction, times how much normal force there is, but that would have to be mg. So in magnitude, the frictional force is always mu, not always, I hate to say always. As long as nobody's pushing down on it or lifting up on it in any way, then yeah, the frictional force is always mu times m times g. That pulling force is gone, right? This thing is just coasting along on a flat surface now. What would cos of 180 be? Let's see. Cos, turn it on. Cos, there it, cos 180. -1. Cos of 180 is -1. Oh, that's nice, because it turns my answer into a negative number. It's like, that's nice, because actually, does friction do positive work or negative work? Negative. It's removing energy. Like, oh, that's, the math takes care of that. Like, yeah, it's totally cool. It does. So the cos of 180 is really just there to turn your answer into a negative number for you. Total coincidence that I chose a distance of 1 meter, in the sense that there's a -1 and a +1 next to each other. That's just coincidence. And I'd have to stick all those numbers, other numbers in. Mu is 0.5, the mass was 10, g is also 10, another coincidence, times the -1 times the +1. Well, all those things get multiplied. Yep. The 10 times 10 is 100, half of 100 is 50, and the -1, so it'd be -50. Joules. The unit would be joules. So would we verbally say that to each other? As scientists, we'd say that the frictional force did -50 joules of work. While it was on that little patch. Take you to the next idea. How much kinetic energy do you think is left as it leaves that patch and coasts along back into a frictionless area? This is all frictionless. Only frictional area was here. How much kinetic energy do you think does it still have as it's now coasting along in this area? It can't be the same that it had on this side, because we know there's a little bit of slowing effect in here. Just think it through. Think about the concepts. Go back to how much kinetic energy did it originally have? Yeah. How much did it lose in the area that was a patch? I lost 50. I'm teaching you so it makes sense. This is how this all works. It totally makes sense. Like, all right, well, how much is left? Textbooks don't always highlight the sensible part of it. They just kind of sometimes they overlook that, and that's disappointing to me. That would be my next question. How much kinetic energy does it have? Let everybody think about it, Jaden. Good job. How much kinetic energy does block have after it leaves the frictional area? After it, I guess, it leaves the frictional area. Yeah, you had a question, though, or are you trying to tell you the answer? All right, hold up. Good job, though. All right, so we'd recognize that it had 433 joules of energy initially, right? And we know that it's losing 50 joules because of the frictional effect. Stole 50 joules from it of energy and put it into heat. So how much is left? 383 joules is how much it has after frictional area. Could you technically calculate a new speed? Yeah, do that, please. What is the new velocity after it's just left that area? Can't be 9.3. That's what we calculated before. Let everybody try. Hold on. Yep, let everybody try. Unless it's a question. By the way, let me just tell you that what I just explained here, that you're taking how much kinetic energy it originally had and subtracting away some because it was in a frictional area, that's called the Work-Kinetic Energy Theorem. The idea that how much work was done by the frictional force, which was, we concluded it was negative 50 joules, stole 50 joules from it. This fancy Work-Kinetic Energy Theorem states that however much work is done by some force, in this case the friction force, that the kinetic energy will change by that same amount. So if it started with 433 joules of energy, and we know this is how much negative work was done by friction, that the kinetic energy of the block will change by that same amount. It's a pretty straightforward idea, to be honest, in my mind, and I think it's got a very fancy name for it, the Work-Kinetic Energy Theorem. It technically is written like this, but I don't need it today. I don't need that formula today. It distracts from the main sequence of logical ideas. But we come back to that later. It's called the Work-Kinetic Energy Theorem. Delta K represents how much change in kinetic energy there is, and that the change is equal to how much our work was done by friction. This would be, by the way, K final minus K initial. So if you knew how much work was done, which was negative 50, and you knew the initial kinetic energy was 433, then you could solve for K final. Although, am I saying that backwards? Oh yeah, I think so. I would have just left this, since it's negative, so this would actually end up being, that actually gives you, think about that, plus, it's not the right answer. So there's something I'd have to think about there. I think you'd end up having to represent this as a plus, which I don't really like doing, but I'll come back to that in a minute. So conceptually, what is a new V? We get square root of 2K over M. So 383. So now we're going to send it up a ramp. I get, or that is x squared. I get 8.76, not 9.3. That was how fast it was moving before it hit the frictional patch. Makes sense that it should be a little less because it lost some energy to the frictional patch. Now we're moving on to the last phase of this, if we could, in the time I have remaining. Now it's moving along, and now it's going to head up a ramp. And it's moving along with, how much speed was it? What did I just say? 8.76. So it's moving with a speed of 8.76 and sending it up a ramp. These are all common things that you could see on AP. Again, just exposing you to all the ideas today. Let's just say that it's a, let's use 45 degrees this time. No friction. and it's going to come all the way up to some highest point and then stop at some point. You can't keep going forever. Let's just say it stops here. What we're going to ask is, how high do we think it goes? What is they would usually call it the maximum height as a question. Now, I'm going to remind you that potential energy, called gravitational potential energy, depends on how high you are and how much you weigh. This, in ninth grade, I would write P dot E for potential energy. Technically, the symbol for potential energy is actually U. So you should know that for the first time now. That capital U is the symbol we use, like capital F for force, M for mass, U for potential energy. That is the symbol that actually all of the world uses in real physics and engineering. I would put a G under there to represent gravitational potential energy. Depends on how much you weigh times how high you are off the ground. Weight times height. And I'll come back in the next class to explain why that formula is that way. What is weight? mg. H. So how is it usually just written? But mg is really the weight component. So things that are, at the same height, if you have a shelf and there's a heavy box and a light box all sitting on the same shelf, they're all the same height, the heavier one's going to have more energy. If they both fell off the shelf and one landed on one foot, the other landed on the other foot, the heavier one's going to hurt more, right? Because it has more energy at that point than the lighter one. Not more speed, interestingly. They both have the same speed. Both have the same speed, but the heavier one would end up having more kinetic energy. Why? Because it's on the shelf, it has more potential energy. On the other hand, if you have two equal weights, two boxes that have the same weight, but at different heights, which one has the greater potential energy? The one that's higher up in the air. Even if both boxes have the same weight, the higher one has more potential energy. So in general, that's the two things that matter when you're talking potential energy. So give it a try. Really, what we're thinking is, what kind of energy does it have at this point flying in? It has kinetic energy. What kind of energy is that going to turn into as it rides up this ramp? Potential energy. You got it. If there's no friction, then there's no loss of energy. That means however much energy it has at the bottom of the ramp, all of that has to turn into potential energy. What am I exposing you to? Really what's called the conservation of energy. The idea that one type of energy can be transformed into a new type of energy without any loss. In the real world, there's always some loss. There's always some friction. But AP Physics 1, they want you to start out somewhere. Assuming there's no friction, that's the question. So what height does it get to? What is max height? Think, well, I've got a formula for potential energy. It has H in it. That would be my thing that I'm solving for. And the conservation of energy idea is just that all the kinetic energy is going to, at the bottom of the hill, is going to turn into potential energy at the top of the hill. And we know that number. You'd have to look back at your calculations. I don't have it right off the top, but not 433 joules. That was the old, what was it? 300 and, what is it? 308, so I'll write that here as 383 joules of kinetic energy. All of it, all 383 turns into potential energy. And there's a nice formula for potential energy. Again, just notice that we're not referencing time. That's one of the beauties of this unit, of this tool. I'm showing you a new tool for calculating things called this whole energy unit. Like there's kinematics, it's one tool, one way of approaching a problem. Usually when you use kinematics, If you use kinematics, it's combined with Newton's second law, usually, A equals F over M. And you can tackle problems that way, but sometimes it takes a long time to solve the problem. You can sometimes say, you know what, heck with that tool. I'm going to use the conservation of energy and solve the same problem in a fraction of the time of your buddy that's taken the other approach, which is kinematics and Newton's law, and you're using conservation of energy approach, and you can do it in 1 minute, and he takes 10 minutes. I'm telling you that once you learn how to use this method, you can usually solve problems that would take a while to do. You can still do them. You'll still get the same answer, but it'll take a while using kinematics and Newton's second law. And instead, you're using this new tool. No time is mentioned. Do we have to think about acceleration? No. Did I have to even think about net force? Nope. That's nice. So this tool means you don't, when you're using this tool, you don't have to use any of those things like net force, acceleration, time. No. Kinematics? No. So I will point out this idea that the total mechanical energy, E stands for total mechanical energy, is K plus U. It's called total mechanical energy. It's just the total energy you possess. All kinetic energy plus potential energy. Conservation of energy is the idea that the total mechanical energy doesn't change if there's no loss of energy due to friction. There is some energy loss to friction. The block can obviously lose some energy. Just doesn't make it disappear out of the universe. It just got turned into heat. The atmosphere absorbed some of it, of the road that it was driving, got frictionally heated, absorbed some of it. So the total energy at the bottom is equal to the total energy at the end. I didn't mean to say that. EI represents the total energy at the bottom is equal to the total energy at the top. This is me exposing you briefly to conservation of energy. You'd write kinetic energy at the bottom plus potential energy at the bottom. That's the total, represents the total energy at the bottom, must be equal to the total energy at the top. In most cases, you can cross two out. At the bottom, how much potential energy does it have? Zero height, zero. Cross that out. At the top, when it stops, how much kinetic energy does it have? None, because it stops. So at the top, what are we left with? 1/2 mv squared, which represents the bottom kinetic energy, must be equal to the potential energy at the top. So technically, we're representing the idea that the kinetic energy at the bottom will be equal to the potential energy at the top, mathematically. And now we can solve. M would cancel out, and I can solve for H. Looks like I would just have to divide by G over here. Divide both sides by G after M goes away. So the velocity at the bottom, I'd end up putting in as 8.76. Squaring it, plugging in, and dividing by 2 times 10. I get 3.84 meters. So the total maximum height ends up being 3.84 meters. How much potential energy will it have at that point? 383, the total kinetic energy that has at the bottom. Where does it have the greatest total mechanical energy? Nowhere. The total mechanical energy here is 383 because there's no potential. The total mechanical energy up here is also 383 because there's no kinetic. Same total mechanical energy in both cases. I want to quickly, in my last seconds, I did have a chance to say this to my last class, throw one other thing in there if I can. If there's a spring here, and this thing comes back down this ramp and compresses a spring, because I did say we're going to return to, and eventually it compresses the spring. It's going to fly down the ramp and compress the spring. The amount of energy stored in a spring, at least if you can take note of the formula, is 1/2 times the spring constant. I know it's been a little while since you did that lab, but it comes back. Hooke's law and springs. 1/2 K times however far it's been compressed or stretched. That would be this distance here. Delta X, again, remember, is the compression distance or the stretch distance. So technically, if they said, all right, now it's going to head back down, and when it fully compresses the spring, how much energy is stored in the spring? 383, yep. So you're like, all right, so I can plug in 383 here? Yep. If they say K is, whatever K might be, K is 100, the number 100, can you technically solve for this variable, which is how far it compresses? Technically you can. Yep, that becomes your unknown. You saw a lot today, but I'm glad. You saw many of the different parts, all from the beginning all the way to the end. Again, I don't learn it all in one day. But as we go through the remaining classes for this unit, I'm going to have you obviously get more time to practice those parts. Any questions at home? Questions at home? Maybe I get to turn my face on one more time. Yep. All right. If no questions from anyone, I'm going to post some problems for you to try. I don't know if I'm going to post a CK12. I may or may not. I'm leaning against it this time, but I might. I may. So just check online, and I'm going to probably post a handful of problems this time from that textbook that I was showing you, the recommended text. I think I'm going to assign 4 or 5 problems from the text that you can try relating to the topic from today. Bye, Zoe. Bye, Zoe. Okay, no questions, anybody? All right, see you later. Have a great day. Bye-bye.